All right, welcome to this first video for this unit where we're going to talk about ionic compounds and how ionic compounds are formed in the way that bonds are formed between a metal and a non-metal. And so if you take a look at the picture here, this is actually something similar to what we've learned in previous units. And so in Unit 4 particularly, we learned how sodium has one valence electron. It'll lose that one valence electron. Fluorine has 7 valence electrons and it will gain 1 valence electron. Now what ends up happening is sodium, when it loses its one negative electron, it's losing negative, so it becomes positive. Fluorine, when it's gaining the negative electron, it becomes negative because it's gaining a negative electron. And what ends up happening is because sodium is positive and fluorine is negative, opposites attract and they come together. Now, the way that I sort of think about it is I sort of think about it like magnets. And so when a positive and a negative, when a positive cation and a negative anion come together, you can think of it like a magnet. And so you have these magnets and they're kind of like positive cations and negative anions, although it works a little bit differently, but you can imagine it like that, and they sort of come together and they're attracted to each other because of the positive and negative charges. So let's go ahead and talk about that. So first off, let's talk about what a chemical bond is. And so we're actually going to talk about 3 types of chemical bonds in this unit. And ionic compounds and ionic bonds are the first chemical bond that we're going to talk about. So a chemical bond is a mutual electrical attraction between the positive charge in the nucleus and the negative charge in the valence electrons. And so it comes down to the valence electrons and what they're doing in the bonds. Something to keep in mind, bonds tend to form so that each atom will gain a full octet, and they'll do that by either losing electrons, gaining electrons, or sharing electrons. And so we'll talk about that, the sharing electrons, in a future video. But again, the whole goal of atoms is to gain 8 valence electrons, and so they will form bonds to do that. Now, the resulting arrangement of electrons does reduce the overall energy of the system, and we'll we'll come back to that later when we talk about bond energies. But essentially, when 2 atoms come together and form a bond, the overall energy of both of them is reduced. And so, again, that concept we'll really talk about later on here. All right, so the electrical attraction between opposite charged ions is called an ionic bond. And so again, like in the beginning there, when you saw the sodium atom losing its valence electron and the fluorine atom gaining that valence electron, those formed ions, and ions are those 2 ions will then come together because of the fact that they're oppositely charged, and that's called an ionic bond. Now, an atom that loses an electron is called a cation. Again, we talked about this before, and they're called cations because cats have paws. And so metals typically lose electrons. And so if you take a look at the staircase here, all of these are metals and they tend to lose electrons. So all of these tend to lose electrons. For the exception of hydrogen, hydrogen can lose electrons, but sometimes it gains electrons as well. So an atom that will gain electrons is called an anion. It's a negative ion, and non-metals tend to gain electrons, and those tend to form anions. And so this staircase here will divide those elements that tend to lose electrons from those elements that tend to gain electrons. Now, ionic bonds will form also between monatomic and polyatomic ions. And so we talked about polyatomic ions before, like nitrate, sulfate, and all that. And so when you look at nitrate is NO3 1 negative. That means it's gained a negative electron. Well, maybe it gained that negative electron from a sodium atom. And so sodium is a positive cation. Nitrate is a negative anion. And again, opposites attract. The ions and ionic compounds, they do exist in a ratio that makes the overall substance neutral. And this is exactly what we're talking about last unit. When we look at magnesium, for example, which makes a 2+ charge, so it makes a 2+ charge. And then we look at chloride, which makes a 1 negative. Because chloride makes a 1 negative, we will need 2 chloride ions to balance the 1 magnesium ion. Now, when those come together, what ends up happening is those will form what is called a formula unit. And so we've talked about the fact that formula units and molecules, one is for ionic compounds, one is for covalent. And so what we're going to do is we're going to talk about how formula units are different than molecular or molecules. So if you take a look here, this happens to be what a sodium chloride structure will look like. And so if you take a look here, the sodium is positively charged, the chloride is negatively charged, and you've got the atoms, the ions surrounding each other. So take a look at that middle sodium there. Notice how it's surrounded by the chloride ions. And so there's an attraction to all of them. It's not that it's attracted to just one chloride, it's actually attracted to all of them. And then if you take a look at the chlorides are also surrounded by sodium atoms. And so really this here is a great representation of how formula units work, because if you take a look, these aren't really bonded to any one magnet, if you will. They're attracted to all each other, and so they kind of you can take them apart, right, and then put them back together, and they're attracted again not just to one atom. It's not just one sodium and one chloride, but they're attracted to many different ones. And so the other thing really to keep in mind as well is that because they're attracted to many different ones, and I'm kind of repeating myself here, but they're not really bonded to any one particular atom. They're kind of really attracted to many different ones. So anyways, and we'll compare that more when we talk about covalent compounds. So Lewis valence dot symbols can be used to represent the movement of electrons from the metal atom to the non-metal. And so this was kind of like what the first slide was showing, where we had the 1 valence electron of sodium transferring to the fluorine. And so here's 3 examples of that. Notice in the first example we have potassium, which has 1 valence electron, and then sulfur, which has 6 valence electrons. Now remember, all atoms want to have 8 valence electrons, so if sulfur has 6, that means it wants to gain 2 more. But if potassium only has 1 to give, well, that's why we need 2 potassiums, because each one is going to give an electron to sulfur. Now notice how it becomes S2 minus, and then each potassium becomes a 1 positive, and the formula is K2S. So this is actually very similar to what we learned before, and so we're just kind of putting a layer of information on there. Look at magnesium and oxygen. Magnesium has 2 to give. Oxygen wants to receive 2, so a 1-to-1 ratio is perfect. And then the last one there, notice how the fluorine wants to gain 1 electron, and so you need 3 fluorines to gain the 3 valence electrons, and so that's how you end up with a 1-to-3 ratio. So the key here is notice what are the electrons doing. This is what we want to ask ourselves. What are the electrons doing? The electrons are transferring. Now, the ions in an ionic compound will arrange themselves in such a way to reduce their potential energy. And again, they kind of they come together to where they are surrounded by a bunch of different ions that they're attracted to. And this arrangement that they make is called a crystal lattice. And so again, this is a really great example of maybe how a crystal lattice is. And so it's not perfect. There's a lot of flaws to this example here, but again, you've got these different ions in here that are attracted to other ions. All right, and there is again a picture of a crystal lattice there. All right, now the crystal lattice will maximize the electrostatic attraction of the cations for all of the surrounding anions and leads to the most stable arrangement. And here is another kind of illustration of that crystal lattice. So again, notice if you can imagine the red balls are sodium, and then the blue atoms are chloride. And so you can see that the way they arrange themselves, they orient themselves to where they're surrounded by the ion that is the opposite charge of them. And so again, that's why we call these formula units, because each individual ion is not necessarily bonded to one anion. So one cation is not necessarily bonded to one anion. They're kind of in a group, that crystal lattice, where they're all attracted to the other molecules around. So we'll compare that to covalent compounds in a little bit. So electrostatic attraction, again, is non-directional. So there's no direction, and so there's not a single anion-cation pair. So again, there's not one cation bonded to one anion. They're all kind of attracted to each other. And so that's why we call them formula units and not molecules. And again, we'll come back to that later. Now, we can also predict the strength of attraction between them because of Coulomb's law. And so the first thing we can do is we can talk about the distance between them. And so the force of attraction between charged particles is inversely proportional to the distance. And so as two particles get closer together, there's a stronger force of attraction. And so if you have larger ions, and so I want you to think about this, if you have larger ions, what ends up happening is, let's say we have two ions, so we have a cation and an anion, and they're this large. Well, they can get this close together, but what if they're this large? Well, they're going to be not able to get so close together. And so what happens is, if they're larger, the force of attraction between them is going to be smaller. And so let's go ahead and take a look at this example here. So take a look at the 1 plus and the 1 minus, the two smaller ones, and then take a look at the 1 plus and the 1 minus of the larger ones. The smaller ions are going to have a larger force of attraction because they're able to get closer together. The larger ones are not able to get as close together, so the force of attraction between them is not as great. Now, the other thing, the other way we can predict the strength of attraction is by the charge. And so the larger the charge, the larger the force of attraction. And so greater charge means that the ions are more strongly attracted to each other. So in this particular example, look at the 1 plus and 1 negative, and then look at the 2 plus and the 2 negative right next to each other. So the 2 plus and 2 negative will have a stronger attraction to each other, so that the positive cation and the negative anion will have a stronger force of attraction for the 2 plus and the 2 minus versus the 1 plus and the 1 minus. So again, it's Coulomb's law. So the closer things are together, the stronger the attraction. Also, the larger the charge, the stronger the attraction. And when it comes to ionic compounds, charge is going to be the more important one. And so if you have a larger charge, you're probably going to have a larger force of attraction. And I know that's kind of counterintuitive because we talked about in Unit 4 how it was distance that matters more, but we'll move on. All right, ionic compounds do have high melting points. So if you think about salt, if you put salt in a hot pan, it's going to not really melt. It's going to take a lot of heat energy to melt salt. Ionic compounds are also hard and brittle, kind of like peanut butter brittle. And so if you think about like a big salt crystal, what brittle means is that you can easily break it. They're also, when they dissolve in water, they do conduct electricity. More on that next semester. But again, when they dissolve in water, we call it aqueous. So if we take solid salt, put it in water, it becomes aqueous salt, and it will conduct electricity. And that's it when it comes to ionic compounds. So the main thing here is that they transfer electrons. So electrons are transferred from one atom to another. And when they do that, when they come together, they're not necessarily bonded to one individual atom, but rather they're their own independent ion, and they kind of exist in a crystal lattice where they orient themselves to where they have the maximum sort of attraction to the other ions around there. So go ahead and come with questions and have a great day.